Okay, this is my second attempt at standard 3.2. For this I decided to do problem 3.16, which says, for a spin 1/2 system undergoing Rabi oscillations, assume that the resonance condition omega equals omega naught holds. For part A, it has to solve the differential equations for the coefficients alpha plus or minus of t. It says use the results to find the transform state vector and the state vector, assuming the most general initial system of the state. So from the book, we can find the general differential equation we need to solve. These ones right here, they're given on page 89 of the book. They're their equations 3.95. Essentially, what these are is the regular state vector is written in terms of a c plus and c minus eigenvalue, but we can use the Hamiltonian to transform this, and we get these coefficients alpha and alpha minus. So basically what we want to do is we want to solve this for alpha of t and alpha plus, alpha plus and alpha minus, where this delta omega is equal to omega minus omega naught. So we assume the resonance condition, which is omega equal to omega naught, which will make delta omega 0. So we plug that in our equations, we become this. So you see that we have this first derivative of alpha t is something equal to alpha negative t, and vice versa for the derivative of alpha negative t. We want to get the alpha t derivative in terms of alpha t. To do this, we can take a second time derivative, keeping in mind that the time dependence for the coefficient is e to the negative I omega t over 2 for the positive state, and e to the positive I omega t over 2 for the negative state. We get this again because alpha is a substitute for c of t, which is the one that has this time dependence. This time dependence right here. So take the derivative again, we solve it, and we get second derivative is equal to this in terms of positive alpha direction, and this will have this general solution. Doing the same thing, we can find the negative alpha direction, which will have a very similar general solution, except we notice we get this negative out front of the A. Moving on. Shift this over. Okay. Thus, so from equation 3.92 in the book, we see that the transform state vector, which is the first one we're asked to find, has this general solution. So we simply plug in our values for alpha t, alpha negative t, and the state vector has this solution, where it's very similar, except we see we have this time dependence that we were talking about earlier. This is the c plus of t, which we substitute in for, which we rearranged to get this transform state vector. And now we plug the c plus in back 2 to get the state vector. So we can plug in our values for alpha t and alpha negative of t, and we get this. This is your transform state vector, and this is your state vector. Assuming the initial state of the system, so when t equals 0, it simplifies way down to this, because all of these go away because we have this t equals 0 in the numerator. So we get our transform state becomes this, and our vector state becomes this. A spin 1/2 system has this general initial state, so we can set them equal to each other, and we can solve, and we get A equals this, and B equals this, and then we can simply plug these back in up here, and that will give us the state vector, the transform vector and the state vector, which we are asked to find for a general initial state. Alright, moving on to part B, we're asked to verify that pi pulse, which is omega 1 times t equals pi, produces a complete spin flip. We have to calculate both the state vector, the transform state vector, and the state vector. So we plug in for our t values. Just we can sort of rearrange this. We plug in for t, and using our transform state that we found earlier, we can work through this, and we get it down to this transform state is equal to this right here, where we notice this is a prime. We see this little relation. The big difference between u prime and u is that it has a z component of times -1. So we have a flip. We have a complete flip. Similarly, we can plug in for we can plug this. Sorry, I'm going the wrong one. We can plug this t dependence into the state vector. We get this. When we do this, the spin up and down possibilities get flipped. So we see again that the pi poles will produce a complete spin flip. Moving on, for part C, it says to assume that the interaction time is such that omega 1 times t equals pi over 2, and that's to find the effect on the system if the initial state is spin up in the z direction. So if we have the initial state, if we have this initial state, our a and b will become 1/2. Sorry, I misspoke there. It's not because of initial state. It's because we have when we plug in this pi over 2, we get the cosines and sines cancel out in the a and b equations above, and we just get a equals 1/2 and b equals 1/2. So plugging that in, we have that our transform state vector is equal to this. Our regular state vector is equal to this. Let me just expand this a little so you can see the bottom. There we go. So this is what we get for the transformed and regular state vector. And moving on, so we can see in the rotating frame, it went from spin up in the z direction to spin down in the y direction with a pi over 2 rotation. This causes the initial state to rotate down to the xy plane and then rotate around the z-axis at omega. And then for part D, you're asked to discuss the differences between the original reference frame and the rotating reference frame in light of the results. If we look back at the results, you can see that in the original frame, the state vector rotates in a time-dependent manner because it always depends on omega. But we see that in the rotating frame, it is fixed. It's just a pi over 2 rotation, or just a pi rotation, and that's because it's time dependent. It's time independent. So the big difference between the original frame and the rotating frame is that it is time dependent for the original frame, but time independent for the rotating frame. And that is it for problem 3.16.